Well, thank you very much. And I'm happy to be here. I appreciate being invited. So I need to take a minute and share my screen. Well, I would like to talk tonight about one of my favorite topics, namely comets. I'll give some general background and then describe the 3 space missions to comets, 2 of which I was directly involved in. Whoops, now we just have to be able to somehow enable the screen sharing. There we go. Yes, no. A large, impressive comet appears generally about once a decade. These bright objects are coming from far out in our solar system, and usually it means they're coming close to the sun for the first time. So if the object is covered with icy volatiles, it's getting heated for the first time. So all these ices then sublimate and drag off a lot of solid material. And that's what makes this great display, the way you see here for Comet McNaught, which was a southern hemisphere comet. Before modern times, comets were feared and their appearance was considered a bad omen. Here is a woodcut depicting the Great Comet of 1577 as seen from the city of Prague. And there are the city's elders gathered on a hilltop. I guess they're discussing what this comet omen means for Prague. But there you have a little bit of artistic license with this great comet streaming across the sky. And you see one of the noblemen there is actually drawing the comet. Yeah. At that time, comets were considered to be phenomena in the Earth's atmosphere. It took 3 individuals over the next 150 years to demonstrate that comets are really celestial objects in orbit well away from the Earth. The first of these was Tycho Brahe, the great Danish astronomer who observed the comet of 1577 that was frightening the citizens of Prague from his observatory at Uraniborg. Here is a depiction of Tycho's quadrant. At that time, it was before the invention of telescopes, and so all one could really do was accurately measure the positions of objects in the sky. So there's his quadrant, very carefully marked off in degrees and minutes of arc and so on. And you see that little eyepiece that could be slid up and down. So you would sight through the eyepiece until you had positioned the object of interest, and that would tell you what the altitude was. And then the quadrant could be moved so that you could also then measure the azimuth. So Tycho Brahe compared the comet's position relative to nearby stars and the moon with near simultaneous measurements from an astronomer in Prague. Since there was no parallax observed, he concluded that the comet could not be in the atmosphere, but was at least 3 times as far away as the moon. That might seem obvious to us to make that test. I mean, after all, supposing you saw a really pretty cloud high in the sky directly overhead, you would not call a friend 50 miles away and say, oh, look overhead to see this pretty cloud, because being in the atmosphere, it would be at a very different angle from somebody that was many miles away. And the same thing would have been true with his colleague in Prague. The comet would not have appeared to be projected at the same position relative to the moon and nearby stars, if indeed it was really in the atmosphere. So that may seem obvious to us, but stop and think, if you had lived in the 16th century when everyone was afraid of comets and so on, would you have really thought to do that test? Yeah. Fortunately, Tycho did, but it really was a century later that Isaac Newton explained comets as bona fide members of the solar system moving in orbits under the influence of the sun's gravity. And then Edmund Halley took Newton's equations and after what he called long and prodigious calculations, all having to be done without the aid of computers, of course, he calculated the orbits of certain comets that had been observed and their positions recorded, and discovered that a comet seen in 1682 had the same orbit as two previous comets some years back, and he concluded it was the same comet with a period of 76 years. So he predicted its return in 1758. Well, Halley died before he was able to see if the comet returned, but return it did. It was discovered on Christmas night in 1758, and so now it bears his name and has come round and been recorded by humans ever since 2 or 3 centuries BC for every 76-year apparition. And I'm sure it had come many times prior to that. This is a diagram of the solar nebula, the disk of gases and solid grains surrounding the young sun. And so as the sun was forming and heating up, it meant that material that was near to the sun in the inner part of the solar nebula would be experiencing quite high temperatures. So any hydrogen compounds, and especially water, would be in the vapor stage and wouldn't be able to condense into ices. So in the inner part of the solar system, you would have mineral grains, different kinds of silicates or iron oxides or iron sulfide or metals and so on, but you would not have icy material. At larger distance, beyond the so-called frost line, then the hydrogen compounds, including water, would be cold enough that they would condense into ices. And that would mean you'd have much more material for forming solid bodies by slow collisions and gradually sweeping things together and so on. That's where there are giant planets, Jupiter, Saturn, Uranus, and Neptune formed. And that's where we think that comets formed. In the process of formation, as the giant planet Jupiter was forming, any smaller planetesimals that passed too close to Jupiter would have their orbits greatly distorted by Jupiter, and many of them would then have their orbits distorted so that they were either ejected altogether from the solar nebula or tossed out to very large distances at the limit of the sun's gravity. The comets we see today come from 2 reservoirs. The Kuiper Belt is the region of the solar system beyond the orbit of Neptune from about 30 to 100 AU, where 1 AU is the distance of Earth from the sun. It's populated by a large number of icy objects. And this is actually a diagram that shows objects which were observed. So hundreds of these have actually been discovered by long exposures on telescopes. And we think that most of them were formed in the region where they now reside or slightly closer around the orbits of Uranus and Neptune. Far beyond the Kuiper Belt is the Oort cloud. We think there are billions or even trillions of icy bodies orbiting in the cold and dark at the limit of the sun's gravitational influence. And as I say, most of these were ones then that had been scattered by Jupiter in the early solar system days, because there was never enough material at such large distances from the sun that they could have formed in situ. And it's these bright comets that probably come from this vast collection in the Oort cloud when one of them suffers some gravitational perturbation. So comets put on a great show out of practically nothing. The nucleus is hidden from view in the glow of the extended coma. So in an active comet, like Comet Hale-Bopp was, and probably a number of you saw Hale-Bopp, the comet has come in and probably has quite a load of icy material close to the surface, which sublimates eagerly as the temperature increases. The gases fluoresce in the sunlight. Solid grains of all sizes, from microscopic up to probably pebble-sized, are dragged off the nucleus by the sublimating gas, and they scatter sunlight very effectively. So what we see as this huge glow is really just a rather small amount of these fluorescing gases and a swarm of small particles. The blue that you see, that's called the ion tail, that comes from a molecular fragment called CN that has an emission line in the blue spectral region. So in fact, we didn't really know what the central body was until Fred Whipple in 1950 showed that comet activity could be explained by the sublimation of water ice from an icy conglomerate nucleus that was only a few kilometers in size. The sublimation rate, say, of water ice or other volatile ices, can be calculated as a function of temperature. It can be measured in the lab. And then you can calculate how hot the surface would get as a function of the comet's distance from the sun. And that all seemed to fit together with an object in the surface area just a few kilometers in size. So that means that then when sunlight hits this solid body, that's a mixture of ices and rocky material, the ices would be heated enough to sublimate, and then the solid grains would be dragged off with the gas. But at that point, we certainly had never seen a comet nucleus directly. But it means that comets then are the leftover icy planetesimals from the early solar system. They were formed at the large distances of the sun where everything was very cold and stayed at large distances. So comets preserve a frozen record of the chemistry of the early solar system. And that's what really makes them interesting, I'd say, to the professional astronomers. Then one can ask, do comets preserve a frozen record of the interstellar cloud from which we formed? Are some of the grains in comets actually older than the solar system? And do they come from a pre-existing interstellar cloud? And that was what originally interested me. I'd been working on the interstellar medium, and so I thought, oh my, comets are just the interstellar medium brought up close to study. That sounds really interesting. So how do we study comets? Well, from Earth, one thing we can do then is take spectra. So here is a typical example of the spectrum from the coma of an active comet, with blue on the left and red on the right here. And what you have is emission lines from molecular fragments of common gases. They're labeled here, and you can see that they are mostly the elements, what we call the CHON elements: hydrogen, carbon, nitrogen, and oxygen. And these indeed are the common elements that make up living things as well. So that, of course, is of great interest to us. But these are fragments. It means that the parent molecules have already been dissociated, and as the gases move out through the atmosphere. When Comet Halley was approaching its 1986 perihelion, so around 1980, scientists all over the world lobbied for sending space missions to the comets. Well, President Reagan was not particularly interested in comets, so the US sent just 2 small particles and field spacecraft that already existed. But the Soviet Union diverted 2 large spacecraft from planned Venus missions to go and fly past Comet Halley and take measurements. And then the European Space Agency, ESA, they planned a mission that would penetrate to the inner coma, daringly close to the nucleus, in the hopes of sampling the elusive parent molecules and directly imaging the nucleus. So this is a picture of the spacecraft. And on the right-hand side is the forward direction. And there is a dust shield there. You're going to go by at a very high speed and don't want these small dust particles to penetrate and damage the instruments. So there was a dust shield, and it was instrumented with piezoelectric detectors to detect the impacts. And that was the experiment that I was working on. DIDSI, it was called, Dust Impact Detection System. And tucked behind that dust shield then were a couple of spectrographs, an imaging system, a dust analysis instrument, and so on, and other electronics. Then you have the solar panels that wrap around the spinning spacecraft and the antenna in the back to transmit the data toward the Earth. The encounter occurred in March of 1986, shortly after the comet's perihelion, at a flyby speed of 68 kilometers per second. You know, blink, and you've already traveled 68 kilometers. So that's partly because Comet Halley has a retrograde orbit as opposed to most objects in the solar system. And the flyby distance was an amazingly close 600 kilometers deep into that coma of gases and solid particles. Well, this encounter was, I must say, one of the most exciting nights of my life. The data were being collected at the station in Darmstadt, Germany. So there was one building where the telemetry was being collected and fed into large computers for storage and so on. But that was an era when PCs were just coming in. So in a separate building, the administrators had dedicated a floor to the experimenters. So each experiment had an individual room, and they could set up their computers, and the data for their experiment would be fed to those computers. So for a couple of days, it was very exciting anticipation as everyone was setting up and more people arrived. And then the Soviet scientists from Moscow arrived, all excited because their mission had been a success, although at much larger distances from the nucleus. And so by the evening of encounter, it was pretty crowded there, pretty exciting, almost bedlam. And then as the comet and the spacecraft sped closer to each other, things quieted down. The experimenters disappeared into their individual rooms, and we, in the DIDSI room, started detecting some dust impacts on the front shield. And as the comet grew and spacecraft grew closer, the rate of impacts increased. And then suddenly, just 7 seconds before the closest approach, everything went silent. And it turned out that what had happened was that a particle of about 1 gram in mass had hit the edge of the dust shield and introduced a wobble in the spacecraft so that the antenna was no longer Earth pointed and we couldn't receive the data. Well, this had been anticipated that it might happen, and so there was a damper system on board, but it took a half hour to an hour to damp out the wobble and get the antenna firmly Earth pointed again. So all of us came out of our various rooms, and we all hastened to the imaging room because we eagerly wanted to see what had the imaging system seen. You know, was there a nucleus? Was there not? So we hastened into the room, and there on the TV screen was displayed a false color image. Well, you couldn't tell much, you know, the different colors represented different brightnesses, but it didn't mean anything really. And then somebody reached up and turned off the color. So there was a black and white image, and we all gasped. Because now you have to look very closely at this. If you're far from the screen, you better just come up closely, because in the center, you see a little tiny black object, and that is the nucleus of Comet Halley. So in all of human history, this comet has come around, you know, umpteen times every 76 years, and now for the first time, this small group of humans was getting a glimpse of the actual nucleus. It was really exciting. And Fred Whipple 36 years after he had proposed his model, was there, and he was as excited as a little kid, just dancing around the room. It was really the most exciting moment of the mission there in the middle of the night in German time. And so now I will show you the processed image that the imaging experimenters put together after the fact from all of their images. And so here you have the comet nucleus. It's about 15 kilometers long. That would be about, 9 miles or so long, and about half that size in the other dimension. As you can see, that the gases and solid grains too are coming off only from the sunlit side. That's the side that's getting heated, and only from very specific limited areas there, not just a huge swarm, but you can see very specific things. And we think that is where there are specific vents or cracks in the surface, and the ices are below the actual surface. And so they're getting heated, they vaporize, and then they find their way out, as I say, through the cracks and vents. The surface was very dark, low albedo, as we would say, and it was also quite warm based on the measured infrared emission. So therefore, the surface was definitely not ice. The ice had to be below the surface, and that makes sense. The comets come around so many times that any ices that had been really at the surface would long since have sublimated away. So the comet was actually ejecting about 3 tons per second at that time. After Halley, there were several spacecraft flybys of short period comets, but what we really wanted was to bring back a sample of comet material that we could analyze in the lab. So on to Stardust. Our group at JPL proposed a sample return for NASA's series of Explorer missions, which were relatively sort of what you might call the simplest class of missions. And so if we wanted to keep it relatively simple, we really couldn't design a complex lander that would have to land and then be ejected. So that we...
I was being pain. I know.
Yeah. Hello? Is it okay? Yeah, all right.
Which way are you going?
Yeah, all right. Is there a problem? I'm just hearing some talk.
No, I'm sorry. I think somebody on the Zoom call has their mic unmuted. It looks like you muted it.
All right, thanks, Dan. Okay, so we proposed to do a slow flyby of a short period comet and then collect a sample of the solid grains being shed from the comet as we passed by. Well, how does one capture intact particles? The little picture on the right of a grain there is a dust grain that was captured in Earth's stratosphere. The bar at the bottom is 1 micron in size. So this little particle is made up of a conglomerate of sub-micron sized grains, all sort of glued together with a few sort of larger silicate crystals there. And we think this might be typical of cometary grains. The Earth is always sweeping up particles, and many of them are indeed shed from comets and are just orbiting out there until Earth comes along. But and then the person pictured there is Dr. Peter Tso at JPL. And every project has to have someone as the driving force. And for Stardust, that was Peter. And he reasoned that, well, if Earth's stratosphere at low densities could slow down these speeding particles and then allow intact capture of them, well, if you could come up with a low density material, you should be able to do the same thing. And so he was suggesting silica aerogel, which is a very low density material. Here is the sign that was above Peter's desk. Have a great idea, be persistent for a decade. And so he had this idea first, everyone was just dubious, but he was persistent. So here is the aerogel. It has a density of only about 0.05 compared to water being 1. But would it capture particles intact? So Peter took his aerogel samples up to NASA's test facility, and 50 to 100 micron iron sulfide particles were accelerated to 6 kilometers per second and impacted the surface of the aerogel that you see here. And you see the damage track in the silica aerogel, and at the bottom, there's the particles. So he proved it worked. We submitted our proposal then, and it was accepted by NASA. Well, here is a diagram or picture of the spacecraft. The blue are the big solar panels. On the front, the little black rectangles are the dust shields to prevent damage to the solar panels, and then there's a dust shield, all the instruments inside that brown rectangle. And at the back, there is the sample collector looking like a tennis racket sticking up, and the capsule that it folds back into that would then be returned to Earth. Here's what it looked like during assembly in the lab, so you can see the size. And you look at the left-hand panel, and the solar panels are folded in thirds, and there are those dust shields perched on the top. There is the sample return capsule with its white cap up at the top. And you see the antenna to communicating with Earth. And then in the right-hand picture, you can see the complexity of putting together a spacecraft, all the wiring, all the electronics, all the instruments, everything that has to be really assembled in the most compact possible way in order to fit inside the dimensions of the spacecraft. Now, here is the sample collector. The aerogel, we decided not to try to make a large chunk of aerogel to send. It's strong material in the sense of its silica, but it's very crumbly and friable. And so instead we use little cubes that fit inside this sort of tennis racket, you might say, because those would be a lot easier to work with. So take a good look at this as it's being enclosed in the return capsule for the final time, and see how shiny it looks there. Launch day came in February of 1999, and the spacecraft was successfully launched on a 7-year journey whose ultimate success depended on the final 1 hour, whether the sample would be returned safely. The spacecraft then had to make 3 loops around the sun. It had to be launched. It essentially has Earth's velocity when it's launched, and then its speed and orbit had to be tailored in order to encounter the comet. The comet was Wild 2 there, whose orbit is shown in the red ellipse. I mean, there was nothing special about Wild 2, except that it was in the right place at the right time. Indeed, JPL's navigation team really had to work hard to find a comet where a spacecraft could pass by at relatively low speed and then return to Earth within a finite length of time. So this was the trajectory that the spacecraft followed for the 7 years. And then, let's see, we got to Comet Wild 2 in the beginning of 2004, shortly after the comet's perihelion, and it was a distance beyond Mars, but inside the asteroid belt. And the encounter speed was only 6 kilometers per second. Well, 6 kilometers per second is 13,000 miles per hour. And so that was defined as a slow speed. And you see, we were not really very far from the nucleus, but it was a lot less active than Comet Halley. So here's what the nucleus looked like when we saw it up close there. There was only a little bit of activity if this had been a long exposure photograph, then you would have seen some faint jets of gas and dust coming off. But this poor thing looks so battered. I mean, what kind of a history has it had? You see all these craters, and at first, really, we don't know for sure how those craters formed. You know, could they be impact craters? In a way, we don't think so. In part, look at the ones at the top. They're all sort of right next to each other, which is not the way you'd expect an impact to be. They all have flat floors, which could be, you know, an impact into a very porous material, but it could also be somehow the remains of vents and so on. And you notice that the sides of all those craters are quite steep and quite stable, and that means that the material that the nucleus is made out of really does have internal strength. It's not just crumbly, and it's not ices. There's a big cavity at the bottom, and again, we don't know whether that was really an impact or whether that was a place where there'd been kind of a explosive release of volatiles that blasted out a whole hole there. But this object's kind of like a hamburger. It's 5 kilometers diameter in its longest dimension and somewhat flattened in the rest. And again, the albedo was low and the temperature was fairly warm. So again, that means there were not ices at the surface. But the real mission goal was the sample return. So fast forward then to January of 2006, and the spacecraft indeed did come back for a flyby past Earth, and at just the right moment, at just the right speed, and just the right orientation with heat shield facing forward, the return capsule was released, and it came streaking in like a meteor, as you can see there. And the parachute opened and it landed safely in the Air Force's Utah test range. And the Air Force guys went out in the helicopter in the night, heard the radio beacon, and picked up the precious capsule. And 2 hours later, a blizzard began. So we were quite lucky in the timing with the weather. And so this capsule then had traveled for 4.5 billion kilometers in those 7 years. And my question to you would be, how far had you traveled in those 7 years? And so maybe I'll save that question for our question time at the end. And so jot down what you think is your guess for how far you traveled in those 7 years. Right. And here then, the sample return had arrived at Johnson Space Center. And what was amazing to me is the collector there, the aluminum collector, looked just as shiny as when it was tucked into the capsule 7 years earlier. So then the aerogel cubes were one by one carefully removed from the collector and examined with microscope, and particles identified, and then a little slice of aerogel removed so that then the particles could be analyzed by microprobes and so on at laboratories all around the world. So what did we learn then? Well, what was surprising was that the comet dust, the particles that were captured, and they ranged from sort of microns, a few microns in size, to chunks that were somewhat larger, but still, you know, rather small chunks. And they ranged from all kinds of things. There was these kind of small glassy particles. There were some solid grains that clearly had to have formed at high temperatures, not out where the icy materials would have formed in the solar nebula. There were some larger pieces of what we called chondrules and so on that we see in meteorites. And meteorites, we think, come from asteroids that formed somewhere outside the orbit of Mars. Just sort of at the transition where you could have in some cases had some liquid water vapor condensing. And then there was a lot of carbon-rich material in the solid grains. Remember, I showed you the spectrum that there were a lot of basically carbon compounds in the molecules. There was also an experiment on board that could measure the composition of the couple dozen particles that actually impacted its collector. And again, they found that about half of the material was very carbon rich. So that was one of the big lessons that we have here. But as one author put it when describing how varied all the materials were, you really could picture that solar nebula was a very turbulent place, and he called it a record of the solar system's wild youth. All right. Well, then we've learned quite a bit about the composition of the material shed by a comet, but we would also like to learn more about cometary nuclei. What's their structure? How do they respond to solar heating? Are they all carbon rich? How fast does a nucleus get eroded? And so another bold mission from ESA. ESA planned what they called the Rosetta mission, a mission that would rendezvous with a periodic comet and then coast with it as it went through its perihelion, approach the sun as close as it was going to, and then observe directly how the nucleus responded. So it was launched in 2004, and it was 10 years before it arrived at its comet. And the spacecraft, you see with its big wide solar panels, also carried a small lander that's pictured there. And again, the comet that it went to just is the one that happened to be in the right place at the right time. That's a long name. Comets get named for their discoverers, but we just call it CG. And so this is just a diagram of the complexity of its orbit, because again, you had to slowly but surely tailor the orbit of the spacecraft until it exactly matched the orbit of the comet given by the red ellipse here. And that took a total of 10 years. And here is another diagram. Now it's the kind of olive green. That's the orbit of comet CG. But one of the problems was comet CG gets out to Jupiter's distance at its aphelion, and here's the spacecraft trying to catch up with it. But at those large distances, the solar panels can't generate sufficient power for the instruments. And so in June of 2011, the instruments were all just turned off. Everything except the most fundamental pieces of the electronics on the spacecraft were just turned off, and the spacecraft coasted in silence in the cold out to Jupiter's distance and then back. And it wasn't until approaching the comet then in January of 2014, it was time to turn the instruments back on. And that was the nail-biting moment for all the scientists, because after you've turned your instruments totally off and let it soak in the cold for 2.5 years, is it really going to turn back on? But fortunately, one by one, the instruments came on, they were tested, everything seemed to be working. And after a couple of months, then the spacecraft began to approach the comet. And surprise, look at this comet. It's a double nucleus. It really looks like there had been two separate pieces that had come together at low enough velocity that they merged rather than smashing each other to bits. And as the spacecraft took many images and analyzed it, it really did look like these were two separate entities. The structural lines and layers and everything did not continue across that boundary. So they really think it was initially two separate pieces, although it sure looks now as if it's that neck that's eroding away. Maybe there'll be two separate pieces again. But here's a close-up for you to study for a minute. Again, it's such a complex surface. And you see some of those flat-bottomed craters the way you did on Wild 2, which again makes one suspicious that they're not impact craters, that they're somehow related to the way that the volatiles get ejected. But, I don't know. They all do still have the flat bottoms and the steep sides. And again, that means that the material that the comet is composed of does have strength, although the porosity is very high. The porosity is 60, 70%. It's like maybe holding a piece of charcoal, you might say, very dark, has structure, but very lightweight for its volume. And again, on the right-hand end, is that a place where there was an explosive ejection, or was that really an impact of a smaller body? But this is just amazing at how complex this small object is. And it's just 4 or 5 kilometers long again. And you can see on the left-hand side, this smooth area. Here it is and larger. And it seems to be that a lot of the dusty material, the small grains that get pulled off the nucleus and trained in the gas, hang around and then fall back down onto the nucleus, and that there's actually some horizontal gas movement or wind, you might say. And so that it seems that this is a layer of particles, relatively fine particles, covering up the terrain underneath, and you can still see something of the structure of the underlying terrain. Again, you see that these vertical walls that indicate that their material really does have strength there. Well, the lander had a little problem. When it was released and a safe place supposedly for landing had been found, the lander's harpoons did not fire to anchor it, and instead it bounced. So it bounced for a couple of hours and very low gravity, remember, and then it settled itself at an angle against a wall. And here then is a picture taken from the orbiter really close up, and that little tiny speck inside the red circle is indeed the lander. And you can see it's kind of in the shadows, which meant that it was only very seldom that its solar panels got illuminated by the sun. So after it landed and settled, it operated for 2 days on battery power. But when the battery ran down, then after that, unfortunately, it was only very intermittent when the solar panels got a little bit of juice. But you can see in this close-up something about what the surface is like at the small scale. It's really a very crumbly kind of mess. So although it's got some strength, it looks like it could be rather friable and jumbled together. Don't know. But so the spacecraft then traveled with the comet and observed the activity and how it increased as the comet approached perihelion, and then as the comet receded again. The closest distance that the comet got to the sun was about halfway between the orbits of Earth and Mars there. And here is a picture then after perihelion. What the spacecraft did then was come back in and take a lot of close-up pictures and really studied places where the topography had changed due to the outgassing. And they could see some places where some walls had crumbled and some vents had changed and so on. And after 2 full years of monitoring the comet, then the mission ended with a low impact crash in September of 2016. In addition to learning about the nucleus and its structure and the processes of how it emitted its material at perihelion and so on, there were also then the spectrographic measurements, including the lander was able to take some measurements that revealed 16 different organic compounds, including glycine, which is an amino acid that's essential to life. And there was also one of the dust detectors on the main spacecraft that could measure the composition of particles that impacted it. And it came to the same conclusion that the material really was carbon rich. Here it said that half of the dust mass was carbon rich material. And again, the comet nucleus had low albedo and relatively warm temperatures. So the result is that really it was quite carbon rich. So I'll close then with this final picture of comet Churyumov-Gerasimenko, the two-lobed nucleus there that's just out there cruising in space. And it seems that what we've learned is that the material comprising comets that formed out in the region of Neptune and beyond really is a jumble of all kinds of the material from the solar system. It really is quite a collection with a lot that can be learned, and probably to be learned about interstellar material as well. And it's really quite carbon rich and has a lot of rather complex carbon-based molecules, which is really rather interesting when we start to consider where did the basic molecules and building blocks for life on Earth come from. And I'm excited about the future, the James Webb Telescope, and what it may learn about the composition of the material surrounding other stars that we know have planetary systems. So I'll stop with that, and hopefully you would have some time for questions here.